In this problem, we're going to determine the electric field on an axis that passes perpendicularly through a positively charged disk of uniform surface charge density sigma. To do this, we're going to have to recall the electric field from a ring of charge is equal to K, Q, X over X squared plus R squared to the 3/2. And if you don't remember how we got that, you can look back on the video for ring of charge. And we're going to have to use that result because if we think about this disk as a series of rings that are concentric, that get larger and larger and larger, if we add up all those electric fields from those rings that make up this disk, we'll have the total electric field from the disk. Now, what makes this problem a little bit difficult is as the rings get bigger, the area covered by those rings gets larger, and so they contain more charge. So the dq is constantly changing. And so for the setup for this problem, what we're going to do is to find the electric field from the disk. We're going to integrate all the little electric fields from the rings. So now I'll call that charge on the single ring a dq. And I'm going to do this as the disk goes from as the ring goes from a radius of 0 to a radius of capital R. Now we have to talk about what the sigma means. The sigma is the amount of charge per unit area. And the areas we're concerned with is the area that this ring takes up. And that ring is a circle with a thickness of dr. So I can write dA as 2 pi r, the circumference of that circle, times the thickness of the circle, which is dr. And this allows me to write dq as 2 pi sigma r dr. Now for the first time, I think it's going to be simpler if we replace this k with the more fundamental version of the constant 1 over 4 pi e naught. And what this allows us to do is to cancel the pi's. I can turn the 2 over the 4 into a 1 over 2. E naught's in the denominator. Sigma and x can come out as their constants. And I'm left with the integral of r dr over x squared plus r squared to the 3/2. I think this is easier to write as a product. So sigma x over 2 e naught, the integral of r x squared plus r squared to the negative 3/2 dr. And we're going to have to use some u substitution. So let's let u equal to x squared plus r squared. So that du would be equal to 2r dr. Keep in mind r is the variable. R is the thing that's changing as the disk gets larger and larger. X is a constant. That's the distance from the ring. And so we can write dr as du over 2r, and I'll substitute that in over here. So I can rewrite this as sigma x over 2 e naught integral of r u to the negative 3/2 du over 2r. That cancels out one of the r's and turns this into sigma x over 4 e naught, the integral of u to the negative 3/2 du. And we know this integral we can do by the power rule is u to the negative 1/2 divided by negative 1/2. So I can make this sigma x u to the negative 1/2 over negative 2 e naught. I'm putting back my original variable for u. And And I need to evaluate this from the smallest radius of 0 to the largest radius of capital R. Right, let me copy that over to the next screen. Okay, now I'll plug in the limits of my integration. Okay, we can simplify that a little bit. So for one, I can switch which one's negative and positive by distributing the negative sign here. So I'll turn that into a positive, and I can make it negative 1 over x squared to the 1/2. I can just write it as x. I'm going to incorporate the x from here into these terms. Right, and so this can be written as sigma over 2 e naught, 1 minus x over x squared plus r squared to the 1/2. Now we're always going to want to graph these things, and it's going to be easy if we graph it if we know the limits as x gets very large and as x gets very small. So as x gets very large, then when we look at this, the r becomes insignificant. And so we'll have x over x squared to the 1/2, which is just x, and so we'll have basically 1. So in the parentheses, if this becomes 1, we have 1 minus 1 is 0, and so we know the electric field as we get very far away drops towards 0. Or I should say goes towards 0. As x gets very small compared to r, if x is very small compared to r, then this term goes to 0. If this term goes to 0, the electric field approaches sigma over 2 e naught. And so that allows me to draw my graph for the electric field as a function of distance from the disk to look something like this. Approaching 0 as x gets very big, and approaching sigma over 2 e naught as we get very close to the disk. This will help us analyze what the electric field should be like between parallel plates. So if we have a single plate that's positively charged, and it's really large compared to the distance we are away from it, we can consider this to be like a disk that we're very, very close to. And it would create an electric field that points away from it because it's positively charged. And the strength of that electric field, so long as we're very close to it, where the distance from it can be considered close to 0 and negligible compared to the radius or the size of the disk or the plate, then you know the electric field is going to be sigma over 2 e naught. Now let's insert a second plate, but this time we'll make it negatively charged. This creates an electric field towards that negative plate. Oh. And it should be of the same magnitude, sigma over 2 e naught. When we consider the electric fields from both of these plates combined, we can see in this region over here, the electric fields would cancel out. We see in this region here, the electric fields are both pointed from the positive plate to the negative plate. And so we should add up those two electric fields to get a total electric field of sigma over E naught. And over here, we see that the electric fields are in opposite directions, and so they cancel out. And so the electric field between parallel plates is uniform and has a value of the surface charge density over E naught, whereas outside the parallel plates, the electric field is 0.